Hey everyone, and welcome back to the channel. Today, we're diving into one of the most fundamental topics in natural language processing. We're going to demystify three essential techniques: bag of words, TF-IDF, and co-occurrence matrices. If you're just starting with NLP or wondering how computers actually read and understand text, this video is for you. Let's get started. So first things first, why do we even need these techniques? Here's the problem. Machine learning models work with numbers, not words. They need numerical inputs to learn patterns and make predictions. But our text data, it's just, text. When we have a sentence like, "The dog sat on the mat," a computer can't process this directly. It needs numbers. That's where feature extraction comes in. We transform text into numerical vectors, arrays of numbers that capture information about the text. These vectors are what machine learning models can actually work with. Today, we're covering three powerful techniques that do exactly this transformation. First, we have bag of words, the simplest approach that just counts words. It's quick, transparent, and surprisingly effective for many tasks. Next is TF-IDF, which is smarter about weighting words. It highlights important terms and reduces the impact of common words. And finally, co-occurrence matrices, which go a step further by capturing relationships between words and giving us context. Each technique solves different problems, and by the end of this video, you'll know exactly when to use each one. Let's dive into the details. Let's start with bag of words, or BOW for short. The core concept here is beautifully simple. Treat your document as a bag of words. Literally just toss all the words in, count how often each one appears, and completely ignore grammar and word order. The process has three main steps. First, we pre-process our text, converting to lowercase, removing punctuation, tokenizing into individual words, and removing common stop words like the and. Second, we build our vocabulary by listing all unique words across all our documents. And third, we represent each document as a vector, basically a list of numbers where each number is the frequency of a word from our vocabulary. Let's see this in action with an example. Here's a simple example with three sentences about pets. We have the dog sat, the cat sat, and the dog barked. After pre-processing and building our vocabulary, we get these 5 unique words: barked, cat, dog, sat, and the. Now look at this matrix. Each row is one of our documents, and each column represents a word from our vocabulary. The numbers? They're simply counts. Document 1, the dog sat, has 0 barked, 0 cat, 1 dog, 1 sat, and 1 the. Simple as that. Notice all those zeros? That's what we call a sparse matrix. Most values are 0 because most words don't appear in each document. Now let's see how we actually implement this in Python. Don't worry, it's incredibly easy thanks to scikit-learn. We import count vectorizer from sklearn. This does all the heavy lifting for us. Here's our corpus, just a list of strings, our 3 sentences. We create a count vectorizer object. And this single line, fit transform, does everything. It builds the vocabulary and transforms our text into vectors. When we print get feature names out, we see our vocabulary. And when we print the array, we get that exact matrix we saw before. That's the power of using good libraries. Complex operations become just a few lines of code. So where do we actually use bag of words? It's fantastic for text classification, like spam detection. It works well for sentiment analysis, document clustering, and basically any task where simple word presence matters more than word order. But it does have limitations.
The big one? It completely ignores word order. Dog bites man and man bites dog would have identical representations, even though they mean very different things. It also doesn't capture any meaning or relationships between words, and when you have a large vocabulary, you end up with huge, sparse vectors that can be memory intensive. But don't let these limitations discourage you. Bag of words is still widely used because it's fast, interpretable, and works surprisingly well for many real-world applications. Now, let's level up with TF-IDF, Term Frequency Inverse Document Frequency. This technique improves on bag of words by being smarter about how it weighs words. It's not just about counting anymore, it's about understanding importance. TF, or term frequency, is straightforward. It asks, how often does this word appear in this specific document? The more it appears, the higher the TF. But here's where it gets interesting. IDF, or inverse document frequency, asks, how rare is this word across all documents? The rarer the word, the higher the IDF. When we multiply TF and IDF together, we get a smart weighting system that boosts unique, distinctive words and reduces the impact of common words that appear everywhere. Let's look at the actual formula. Don't worry, it's simpler than it looks. TF-IDF for a word W in document D equals TF times the logarithm of N divided by DF. TF of W in D is just the frequency of that word in that document. We've seen this before. N is the total number of documents in your corpus. And DF of W is the document frequency, how many documents contain this word. The logarithm here is just a mathematical trick to smooth the values. What matters is the intuition. Divide total documents by how many contain the word. If a word appears in every document, you divide by a large number, getting a small IDF. If it appears in just one document, you divide by a small number, getting a large IDF. The result? Important, unique words get higher scores. Let me make this crystal clear with a concrete example. Take the word the. It's everywhere, right? It appears in virtually all documents. So when we calculate its IDF, we're dividing by a large number, the total document count. This gives us a very low IDF and therefore a low TF-IDF score. TF-IDF is essentially saying, hey, this word is too common to be useful for distinguishing documents. Now compare that to a word like quantum. If this appears in only one document out of 100, the IDF shoots up. We're dividing by a small number, giving us a high IDF and a high TF-IDF score. TF-IDF is saying, this word is distinctive. It helps identify what makes this document unique. And that's the magic of TF-IDF. It automatically identifies the most important and distinctive words in your documents. The code for TF-IDF is almost identical to bag of words. We just swap one class for another. Instead of count vectorizer, we import TF-IDF vectorizer. Same corpus, our 3 sentences about pets. Create the TF-IDF vectorizer, same pattern. And fit transform, same method, but now it's calculating those smart TF-IDF weights instead of just counts. The output looks similar, same vocabulary, but notice the values. Instead of simple counts like 0, 1, 2, we get weighted decimal values. These weights reflect how important and distinctive each word is. And that's why we love scikit-learn. Complex algorithms become simple one-liners. So when should you reach for TF-IDF? It's absolutely essential for search engines. When you Google something, TF-IDF helps rank documents. Pages that contain rare query terms get boosted in the rankings. It's also perfect for keyword extraction. Want to automatically identify the most important terms in a document? TF-IDF scores tell you exactly that. And for document similarity, comparing text to find related content, TF-IDF vectors work beautifully with cosine similarity. But remember, TF-IDF still has similar limitations to bag of words. It still ignores word order and context. It can't understand that bank near river is different from bank near money. That's where our third technique comes in. Welcome to Co-occurrence Matrices, where we finally start capturing relationships between words. Here's the core idea. Words that appear together frequently are often related in meaning. If coffee and morning appear near each other constantly, they're probably semantically connected. Think about it. You see coffee and morning together, king and queen together, neural and network together. These co-occurrences aren't random. They tell us something about meaning. To build a co-occurrence matrix, we define a window size, typically 2 to 5 words. This determines how close words need to be to count as co-occurring. In "the cat sat on mat," with a window of 2, cat and sat are within 2 words of each other, so they co-occur. We increment their count in our matrix. We slide this window through our entire text, counting every time words appear together within the window. Let's break down exactly how we build a co-occurrence matrix. Step 1. Pre-process your text. The usual cleaning, tokenizing, all that good stuff we've done before. Step 2. Set your window size. This is a hyperparameter you can tune. Smaller windows capture tighter relationships. Larger windows cast a wider net. Step 3. Slide through the text. For each word, look at its neighbors within the window. Step 4. Count those co-occurrences. Every time word A and word B appear together within the window, increment the cell in your matrix at position A, B. The result is a matrix where each cell tells you how often 2 words appeared together. Let's see a concrete example.
Here's our sample text. The dog sat, the dog barked, the cat sat, with a window size of 2. Now, look at this beautiful matrix. Each row and column represents a word from our vocabulary. Let's decode this. Look at the cell for the and dog. It shows 2. That means the and dog appeared within 2 words of each other twice in our text. Dog and sat shows 1. They co-occurred once. Notice the diagonal is all zeros? That's because we don't count a word co-occurring with itself. That wouldn't be useful. Also notice the matrix is symmetric. The, co-occurring with dog, is the same as dog co-occurring with the. This matrix now captures relationships. We know which words tend to appear together in our text. Now for the implementation. This one's a bit more complex than the previous 2, but I'll walk you through it. We need NumPy for matrix operations and default dictionary for efficient counting. Our function takes a corpus and window size as parameters. First, we build our vocabulary by collecting all unique words across all sentences. Then we create a mapping from words to numeric IDs. This lets us use words as array indices. We initialized our matrix with zeros. It's vocab size by vocab size. Here's where the magic happens. For each sentence, we loop through each word. Then we look ahead within the window size. That's this inner loop with the range function. When we find 2 words within the window, we increment both matrix positions. Remember, it's symmetric. This code might look complex, but trace through it with a small example and it'll click. The logic is straightforward. We're just systematically counting co-occurrences. So why go through all this extra complexity? What do co-occurrence matrices unlock? First and most importantly, they're the foundation for modern word embeddings. Algorithms like Word2Vec and Glove use co-occurrence statistics to learn dense vector representations of words. This was revolutionary for NLP. They help us discover semantic relationships. Words that co-occur frequently are semantically similar or related. This is how we can find synonyms, analogies, and connections automatically. And they're great for topic modeling, identifying themes and topics in large collections of documents. But yes, there are trade-offs. The matrix size grows quadratically. If you have 10,000 words, that's a 10,000 by 10,000 matrix with 100 million cells. That's memory intensive. It also requires more computation than simple counting. You're doing more work to capture more information. But when you need that contextual information, it's absolutely worth it. All right, let's put all 3 techniques side by side so you can see the big picture. In terms of complexity, bag of words is simple. TF-IDF is moderate, and co-occurrence is the most complex. Bag of words and TF-IDF both ignore word order completely. Co-occurrence at least partially captures it through the window mechanism. Same with context. The first two don't capture it at all, but co-occurrence matrices do. Memory usage. Bag of words and TF-IDF are both low because we're just storing sparse vectors. Co-occurrence needs much more because of that large matrix. And here's the key: what each is best for. Bag of words for quick classification when you just need a baseline. TF-IDF for search and ranking when you need smart weighting. Co-occurrence for word embeddings when you need rich relationships. And finally, speed. The simpler methods are faster. Co-occurrence is slower but captures more information. The best technique depends entirely on your specific use case. Let me give you some concrete decision-making guidance here. Reach for bag of words when you need something quick and transparent. Maybe you're building a spam filter and you just need a working baseline. Or you're doing exploratory work and need fast iterations. Or interpretability matters. Bag of words is super easy to explain to non-technical stakeholders. Use TF-IDF when you're building information retrieval systems, search engines, document ranking, recommendation systems based on content similarity. TF-IDF shines here. Also great for automatic keyword extraction when you need to summarize what a document is about. And use co-occurrence matrices when you're doing more advanced NLP, building custom word embeddings, analyzing linguistic patterns, or when understanding word relationships is central to your task. Just make sure you have the computational resources to handle it. In practice, you often start with BO or TF-IDF and only move to co-occurrence if you need that extra contextual power. Let's zoom out and see where these techniques fit in a real NLP project. This is your typical NLP pipeline from start to finish. You start with data collection, scraping websites, loading data sets, whatever your source is. Then, pre-processing. This is crucial. Clean your text, tokenize it, remove stop words, maybe do lemmatization or stemming. Step 3. This is where we are. Feature extraction using bag of words, TF-IDF, or co-occurrence matrices. We're converting that cleaned text into numerical vectors. Then, those vectors go into your model training. Could be traditional ML like support vector machines or neural networks or whatever algorithm fits your problem. Finally, evaluation and deployment. Test your model, optimize it, and get it into production. So these techniques we're learning today, they're not isolated concepts. They're essential pieces of the larger puzzle. All right, let's wrap up with the key takeaways. Bag of words, your simple, fast baseline. Counts words, ignores everything else. Perfect for quick prototyping. TF-IDF, the smart upgrade. Weighs words by importance, highlighting distinctive terms. Your go-to for search and retrieval. Co-occurrence matrices, the context-aware option. Captures word relationships, bridges to word embeddings, more complex but more powerful. These 3 techniques are the building blocks of NLP. Before you jump into transformers and BERT and all the fancy deep learning stuff, make sure you understand these fundamentals. They're still used in production systems today because they work, they're fast, and they're interpretable. Master these basics and you'll have a rock-solid foundation for everything else in NLP. And that's a wrap. From text to numbers, mission accomplished. We've covered 3 essential NLP techniques today: bag of words, TF-IDF, and co-occurrence matrices. You now understand how computers transform raw text into numerical features that machine learning models can actually use. If you want more NLP tutorials, maybe word embeddings, neural networks for text, or transformer models, make sure you hit that subscribe button and ring the bell so you don't miss future videos.
If this video helped you, give it a thumbs up. Drop a comment letting me know what NLP topic you want to see next, and subscribe to support the channel. Thanks so much for watching, and I'll see you in the next video. Happy coding!